Welcome. We started with the microscopic balances in the last lecture, and in that I explained to you how to find the control volume and how to start making the microscopic balances by considering a small control volume. And we did the continuity equation, that is the mass conservation equation, and we started with the momentum conservation. In this lecture, we shall be continuing on that and shall be talking more on these microscopic balances. So, today we shall be covering up something on the momentum balance and something on the energy balance. So, here to continue with the momentum balance, I talked to you about phi in the last lecture. So, in this lecture, I give you the expression for the phi and tell the physical significance. So, phi is basically the total momentum, which is the contribution of three components. So, here you can see that, as I told you in the last lecture, that this total momentum flux is due to the molecular transport and due to the convective transport. So, in the molecular transport, we have the viscous transport and also the contribution due to the pressure, and the convective transport is due to the motion of the fluid, and we will have these different components of this tensor, and you can see here for the x direction we have Pxs equal to this pressure plus tau xx plus rho into Vxx. Similarly, we have phi xy, this is tau xy rho Vx Vy, and phi xz tau xz plus Vx Vz. Now, please understand that there is no pressure term in these two expressions, because pressure always acts normally to a surface and these two represent the parallel to the surface. So, there is no pressure term in these two expressions, and similarly you can also find out the expressions for phi yx, for phi yy, for phi yz, or phi zx, phi zy, and for phi zz. So, in this way you will find that in the three coordinate directions you have this kind of a set of fluxes, and that will be due to the various types of velocity gradients you are having and the pressure changes occurring in the various coordinate directions. So, here you can see in this particular figure what we have tried to demonstrate is how you visualize this kind of momentum transfer due to the this flow or the molecular transfer. So, this is a particular control volume in the rectangular coordinate. So, this is x, this is y, this is z, and this width is delta x, then delta y, and then this is delta z. Okay. So, you can see that we in these three figures they differ the way these forces or these tensors are. See that we have drawn this particular cross sectional area, that is a cut section on to show the yz plane. Here we have shown the xz plane, and here we have shown the zx plane, and each of them you can see that in this case the p dx, as I was telling you, this is acting normally to this, and here on this particular plane you can see p delta y is acting normally to this, and on this particular plane you can see this p delta d is acting normally to the plane. So, that is why you will find that this p term will be appearing only once out of these three tensors. Okay. And also you see that this tau is showing all the shear, and they will come parallel to the surface, and this delta is the Kronecker delta. Perhaps you know that this Kronecker delta will assume value of either 1 or 0 depending on the pair of the vectors, which is pair of directions which are considered. Okay. So, this delta will be ij, we write delta ij equal to 0 if I is not equal to j, and delta ij is equal to 1 if I is equal to j. So, that is the what we call the Kronecker delta. This is 0 if I is not equal to j, and this is 1 if I is equal to j. Okay. So, with this kind of notations you can easily see that how we write for these equations. Okay, and these define that how these particular terms are automatically losing these things. Now let us go to the energy balance equation. Okay. Now in this energy balance equation, it is similar to the one which we have studied for the momentum balance or the mass balance. Here you see that the net change in the energy of a particular system is given by the net of energy coming into the particular system and due to the convection, and then net energy addition by the molecular transport or what we call conduction, and then rate of work done by some molecular mechanism like for stresses, and rate of work done by the external forces, and net of any heat generation or consumption due to some reactions. So when you talk of energy, energy can come in various manners, as we learnt earlier that work will also generate some kind of energy change in the system. And you know that there could be three forms of energy: convection, conduction and radiation, and there could be some reactions which involve either production of energy, heat energy, or the absorption of the heat energy, that is some may be exothermic or some may be endothermic. So all these kinds of things will generate some kind of energy change in the system. So those things have been taken care of in this particular equation. And here I have shown that the kinetic energy is how we put the kinetic energy per unit volume, and then we have the internal energy which is due to the temperature of the system. Now then, to find out the total change, rate of change of the energy in the system is to multiply, because these are the volume specific values. So we multiply with the total volume, and because this volume is constant, so we can take it out of the differential. So we find that this total is the energy change per unit time of the particular system, and then we have this particular term for the left hand side of the conservation equation. And here I have shown that this rho u cap is showing the internal energy per unit volume, and this particular thing is showing the kinetic energy per unit volume of the system. And here we are writing all sorts of energies which are entering or leaving the system. Now please understand, here by E, I will show you later that what this E constitutes. Okay, so E is the effective energy that is either going or coming out of the system. So here we have written that in the x direction something is going and something is coming out, and into delta by delta z gives us a rate, because these things are fluxes. Fluxes into the area of cross section gives the rate. Similarly, for the y direction, this is going in and this is coming out, and z direction, this is going in and this is going out. And you can see here that in this case everything is coming under a single equation, because it is a scalar form. There is no vector, it is a scalar form. Okay, so we are getting only one equation. And now, as I told you that E is the effective energy of a given stream. So it has in it the convective transport of kinetic and internal energy, then heat conduction, and any kind of work associated with the molecular processes. Work, for example, that whenever a fluid is flowing over a surface, it has to work against the drag forces. Okay, so that is the kind of that will lead to some kind of energy exchange. Okay, there will be energy will be dissipated also to overcome this resistance to the flow. Okay, and these kind of things will not be present when we are talking of solid, but under no flow situation this particular energy exchange will not be there. So you can see that depending on the system to system, you will have different types of energy exchanges involved. So the work done is given by this particular thing. It's a dot product of the fluid velocity and the force acting on the fluid, and here by G we do not mean the gravitational force only, we mean any kind of body force on the system and per unit mass. So this is the mass of the system, that is the density into the volume. Okay, so this gives the total amount of force, and this in the dot product with the velocity gives us the work done. Okay, now after putting all the values, we find this is the final expression for the energy balance. Okay. And in this you may also add, in this kind of exchange you can also add any kind of generation terms due to the reactions. So, after doing, if you write that equation in the vectorial notation, you will find that you have this kind of an equation, this scalar equation. Okay, this is a scalar equation. So, in this form you will find that in the scalar equation, but in a vectorial notation, in the sense that, so here you find that we write in vector notation. Vector notation means we are using the operator like nabla here. Okay. So, in the vector notation, this the equations which we have just shown can be written in this form. Okay. And you see that this particular form, whenever we are putting in this nabla form, these become independent of the coordinates. So, even though we derive all the equations in the Cartesian coordinate for ease of our understanding, but all these equations can be represented equivalently in any other coordinate systems. And in this you can see that E has three basic contributions. One is the convective energy flux, then this is the rate of work done, and this is the rate of heat transfer by molecular mechanism, and this pi is the stress tensor. More detail can be found in any book on the transport phenomena, and I have given some references at the end of this lecture. Now, after deriving all the equations for the mass balance, the energy balance and the momentum balance, I just list out is the simplified form of these equations in this particular slide. And first we start with the mass balance. So, this is a mass balance which considers no only it considers the in general a compressible fluid. Okay. That means, if this particular density is within the differential. Now, in case of incompressible fluid, we find the density to be constant. So, this particular thing goes to 0, and so we will be living with only delta dot V, because this rho will also come out of this nabla operator. So, we shall be having only this nabla dot V. Okay. And you can see this particular thing means, in the, if you write in the Cartesian coordinate, it will be coming like dou Vx by dou x plus dou Vy by dou y plus dou Vz by dou z equal to 0. So, this is what you will get for the incompressible flow overall continuity. Okay. Next, we come to the species continuity. In the species continuity, we also derive this particular equation, and here we have the total derivative. This d by dt is the total derivative. This is an operator, you can say. This will be dou by dou t plus v dot nabla. Okay. So, this is the operator d by d, the total derivative, and this is a partial derivative. Okay. So, in this total derivative, we have the contribution for the change at any given location with time, and this gives due to the convective flow. Okay. So, this is the total. So, in this case you can see that if you write, if you expand this one, you can replace this d by dt by this particular terms over here, and you can see you will get the same equation as we have derived earlier, and this particular term gives the contribution of any kind of reaction. Okay. And this gives any kind of diffusive term that is involved in the species transfer. Okay. So, that means this particular derivative includes the convective term, and this includes the diffusive term. Next, we come to the momentum balance, as we have just derived. Again, with some simplifications, we find that this can be written like this. Here we have the change in the velocity, and again you will see that d by dt is same as dou by dou t. Is writing again. So, it is, so this d by dt is again dou by dou t plus v vector dot nabla. So, here again you find that this kind of equation you will find, and here you can see that here we have the pressure gradient, and you know the gradient you will get this particular thing will be coming as dou p by dou x. Okay, like dou p by dou x or dou p by dou y or dou p by dou z. These things, these three things will be there for this, and this is the that surface interaction of stresses, and this is the body force. Okay. So, understand this G is always taken as body force, but not to mean only the gravitational, but any kind of body force acting on the body. And lastly, we derived also the energy balance equation, and this is the form we derived. Okay. Now, what I shall do is this, that I shall just give you the representation of all these equations in the three coordinate systems. So, first let us start with the Cartesian or rectangular coordinates, and here we have the rectangular control volume, and this I explained to you earlier, and for this particular system we derived the equations also. So, here you see the generalized equation for the mass balance, and here I have just expanded that capital D by capital D t term. So, here you have found that this is dou V x by dou t plus V x into dou V x by dou x plus V y into dou V x by dou y plus V z into dou V x by dou z. Okay. So, this particular term is the inertial term or due to the convection term. So, if you find it is there is no flow, so these terms will be going to 0. Okay. Now, I am not explaining all these things because they look similar. Okay. And next I go to, okay, one thing I must tell you about the tau xx, the stress term. For example, if you are talking of the Newtonian fluid, again this stress term will depend on the type of the fluid. Okay. Newtonian fluid, non-Newtonian fluid. So, suppose you talk of Newtonian fluid, so this will give rise to this kind of expressions. You will get mu because you will get this kind of expression you will get. Okay. So, this for Newtonian fluid you will get this kind of expressions, or similar things you can write also for the y direction and also for the z directions. Okay. So, this is special case. So, what I have shown you is some general case. Next we come to the energy balance equation. Here we have the energy balance equation. You can see that here again under this particular thing will give us the conductive balances. So, we can write, if we assume that the thermal conductivity is constant, then this will give rise to, in terms of temperature, this will give rise to the whole thing, dou 2 t by dou y square plus dou 2 t by dou z square, and everything will be with the these are thermal conductivity. Okay. Okay. So, this is how we write it. Okay. Similarly, we have these expressions for the species balance. Again, if you look at these expressions without any derivation of these expressions, we can say that there is something called, like in this case we were using the Fourier's law of heat conduction, Fourier's law of heat conduction to write that expression in terms of the thermal conductivity. Similarly, these things can be written using the Fick's first law of diffusion, okay, which says that all these things, I am not going to the detail of these derivations, it will simply give us diffusivity coefficient d2 say C alpha, or here we are writing omega alpha, it will be omega alpha by dou x square plus d2 omega alpha by dou y square and dou 2 omega alpha by dou z square. Okay. So, this is the diffusivity coefficient, or simply diffusivity. You can sometimes call diffusivity coefficient or diffusion coefficient or simply diffusivity. Okay. Now, understand this, that if in this case, if this d is not constant, it varies with x, or k is not constant, it varies with x, then what we write, that instead of writing this, we write it that dou by dou x d dou w alpha by dou x. Similarly, this also for if it is not constant, then we write it as dou by dou x into k into dou t by dou x. Okay. So, to account for the variation of the diffusivity and the thermal conductivity with location. Okay. So, this is how we write. Now, coming to the equations for the other coordinates, here we have shown the cylindrical coordinate, and in this figure you can see how we represent a cylindrical slice or shell. Here you can see that we are taking these are axis from the axis, and here see that there is a this is the r direction towards this, z remains the z, but theta now sees the what is the rotation, how much rotation we have to give. So, you can see theta can rotate and to 360 degree. Okay. So, it can rotate from this, you can go in 360 degree like in this particular circle. So, you can see here that this small slice, this is the length is delta z, and this small slice is dr. Okay. And this particular thing, this particular width is r d theta. Okay. And you can see here this particular point is r theta z. That means, r is the distance from the central axis, theta is the rotation we have to make from this axis, and z is the distance from this particular plane. Okay. So, that is how we locate, and that is how, and we are moving, this is this particular, we are taking a d theta circulation. So, this particular thing is d theta. Okay. So, we are getting, this is how we are getting this particular control volume, and the volume of the control volume is dr into r d theta into dz. Okay. So, you can derive it, or we can also, I also gave in my earlier lecture the transformation of one system of coordinate to another in nabla form. I showed you the different representation of nabla. So, with those you can easily find out that these are expression for the mass balance, these are for the momentum balance, and similarly we have this for the energy balance, and this is for the species balance. So, please mind it, the whatever I have shown you for the momentum balance, for the stresses, this right hand side, this conductive term and the diffusive term, their things will remain the same, similar laws will be applied, only thing is this, they will be changing the coordinate system. Next we go to the spherical coordinate. In this we consider this a sphere, and as you know, spherical coordinate is represented by one distance and two angles, and here you can see that a particular sphere is spherical slice is considered, and here you can see that how these various types of width are considered. Now, this is the theta direction. Okay, that means this theta will go like this, and this is the phi direction, as you can see. Okay. So, from you can see that easily you can find from geometry that what is the volume of this particular shell, and this volume will come out to dr r d theta r sin theta d phi. Okay. And with this particular thing we can find out the expressions again for the mass balance over here. This is the momentum balance, and this is the energy balance and the species balance. Now, you can see that as we go to from the Cartesian coordinate to cylindrical or spherical, the equations becomes quite complicated. However, please understand that you will find that at times it becomes easier to work with the cylindrical and the spherical coordinate depending on the shape of the particular system. And you will find that even though apparently they look complicated, but in real terms whenever you are going to make the balances, you will find that many of these terms go to 0 if you are providing choosing the appropriate coordinate system, and many times you will find that in the cylindrical coordinate some of the terms go to 0, which will not go to 0 if you stick to the rectangular coordinate by looking at its apparent simplicity. So, whenever you are choosing the particular coordinate system, choose it carefully so that your solution becomes easier and you can you can reduce the complexity of the equation. So, these are the two references which will give you a very good analysis and theoretical concepts on all these momentum balance, mass balance and energy balance. Thank you.